We're now ready to continue our discussion of volumes of revolution. In this video, we're going to explore a different method called cylindrical shells, or just shells for short. Instead of using a disc or a washer, something shaped like, well, a quarter coin, we're instead going to use sort of the idea of like stacking cups, one inside the other, but hollow on the inside. So they're more or less, well, like a tube or a pipe or, well, maybe the toilet paper roll when it's empty. So when you're looking at it and you're examining this shape, what we're going to do is we're going to again divide the region to be revolved. But this time we're going to make the rectangular strips, the division, be parallel to the axis of revolution. And when we do that, we're going to pull that rectangle around in a circle, creating one of these tube shapes where it nests inside of others created from the partition. So for example, you could end up with something like this, where what's on the inside is in fact one of these circular shells. Now it does have a little bit of thickness to it, and that's because this is the original rectangle or strip that we revolved. And this is the differential. When you roll it up like this, it looks like a tube, but if you're to slice it and open it up, it becomes basically a rectangular box, a very, very thin box with the differential dx or dy. In this case, when we're looking at it, we can take the height here as one of the measures of this rectangular box, and this measure here, which is the circumference of that circular shell, when we open it up, becomes the length. So for the rectangle, we have length and we have width, and the thickness is given by the differential. This gives us the circumference times the height times the thickness. This would be 2 pi r for the circumference, h for the height, times the differential. And that gives us the volume of one shell. And we do what we always do. We add all the volumes of all the shells together and take the limit as the number of shells goes to infinity. We'll see that this method is quite different in some ways from the disc washer method. The shell method takes care of things without having to create something like a washer when your area to be revolved does not touch the axis of revolution. We won't have an outer volume and an inner volume and subtract them. Instead, the setup of the problem itself will take care of that and create any hollow space on the inside that might be needed. Let's take a look at some pictures so that you can see more clearly what's happening. In the first picture here, on the left, you can see that we have a function y equal f of x, and underneath it is drawn one representative rectangle, one strip, if you will. This corresponds to the thickness of the shell. We take this and we revolve it around the axis of revolution, which here is the y-axis. Notice that in the shell method, which ends in a double L, the rectangle or strip is parallel to the axis of revolution, and parallel also has a double L in it. When you do this, it creates, well, sort of like a yoga tube or a yoga mat rolled up. And if you have many of these partitions here coiled into shells, you can recreate the shape of the curve, which you can see right here at the top of the picture on the right. This gives us eventually this whole area here that's being revolved around the y-axis, producing this solid of revolution that we see there. We only have 2 learning objectives for this section. The first learning objective is to calculate the volume of a solid by using the method of cylindrical shells. And then we want to take a look at the different methods, the disc method, the washer method, and the shell method, and discuss when it might be appropriate to use one as opposed to another. Let me go ahead and share my screen with you so we can get started. Again, this method of cylindrical shells is most like stacking cups, where you're putting one inside another, but you're approximating the shape of the curve by the relative heights of the shells. And this is almost like a stick of gum being rolled into a tube, or like a yoga mat being rolled into a tube. And we're calculating the volume of the solid created by adding the volume of each individual tube together. Now, the tube, of course, does have volume. While it is very thin, it does have, if you cut it open, length, width, and height. It does become a rectangular box when cut apart. When we look at this, remember that you have to draw the rectangle or the strip partitioning either the X or the Y axis parallel to the axis of rotation. And that means that if you're going to revolve around the Y axis, instead of using the differential dy, the rectangles will be vertical, so the differential will be dx. Revolving around the x-axis or some other horizontal line, however, will require that your rectangles be parallel and also horizontal, which means going around a horizontal line results in the differential dy. Let's take a look at this region here, which is bounded by x squared, the graph, the x-axis, and the vertical line, x equal 4. It's being revolved around the y-axis, which we see here. Let's go ahead and indicate the axis of revolution by drawing that curving arrow on each graph. When you look at the initial graph, what we see is, in fact, the area which is to be revolved. The area is trapped or bounded by x squared, x equal 4, and y equals 0, the x-axis. When we draw our rectangles, they're going to be parallel to the axis of revolution, which means that they are going to be vertical as well. That makes the differential dx. When we compute the volume of one shell, which is, of course, one tube like this, we need to find the circumference of the tube, for which we need the radius. The radius is given by the distance from the axis of revolution to the particular shell. In this case, the radius is actually equal to x, the variable x. Since the differential is dx, we leave it represented as x. The height, however, or length of the rectangle, which gives us, of course, the height of our shell, is measured by the y value on x squared. So when we write the height here is equal to y on x squared. So the height becomes x squared. Because the differential is dx, we have to represent it in terms of the variable in the differential, which is x. This then will give us a volume for one single shell. Notice that for all strips from the left side of the region to the right side of the region have a radius that corresponds to x and a height that corresponds to x squared. There's no need to split the definite integral into more than one. When we compute the volume of one single shell, we can use the formula 2 pi r times the height times the differential. In our case, this becomes 2 pi times x squared times dx, giving us 2 pi x cubed dx for the integrand. In the second picture, you can see that the region is starting to be rotated around the y-axis, and here in the last two pictures, it has been completely rotated. In reality, when we take this shape and we rotate it by taking our partition and curving it around the axis of revolution, in order to get it to meet up exactly, the back edge or outside edge does have to be slightly longer than the inside edge. Otherwise, the edges won't meet together. However, as we take the limit as the number of partitions goes to infinity, the thickness, dx, in this case, will go to 0. And because of that, the lengths of the outer and inner radius of one individual shell will become closer and closer to the same value. And as we take the limit as the number of shells goes to infinity, they become equal. So we do not, in fact, have to worry about the fact that when we coil it into a shell, that the outside radius is slightly different from the inside radius. When we take the limit, they approach each other. Now that we've looked at it, let's take a closer look at a picture that shows the different pieces and how this becomes a rectangular box from a shell. Again, we're going to take the one strip under our function, and we're going to rotate it into a circle. Notice that this point right here, which is on the curve, is given by the coordinates x, y on the function f. X then becomes the radius, but the x value at that particular point, so it becomes like an x sub I. The thickness of the wall itself is the thickness of the original rectangle, which is dx here. When we cut this and we open it up, we get a box. The top length is given by the circumference. This distance around the circle opened up. That has length 2 pi times the radius, but the radius is given by the x value at that point. So it becomes 2 pi x sub I star. Then we can find the height at that particular point. The height at this point is given by the y value on the function. So the height is f of x sub I star. And putting it all together, we have the formula 2 pi x sub I times the function at x sub I, the y value, times the differential dx. You can think of the volume of a single shell as 2 pi, the radius times the height of the shell, multiplied by the differential. When we take this and we add all of these shells together, again, keeping in mind that we're making infinitely many shells and following the shape of the curve with the edges of the shells, and then take the limit as the number of shells goes to infinity, we get the precise volume of the entire solid that's revolved around the axis of revolution. This gives us, of course, a limit of a Riemann sum, and the Riemann sum, of course, is right here. Here is what it looks like for revolving about the y-axis. When you want to revolve about the y-axis, your axis of rotation is vertical. And by the shell method, that means that your strips must also be vertical, so your differential must be dx. Then, to measure the radius, you would take the point where it meets the function and think about the coordinates, x, y. X is the value of the radius, which appears here as 2 pi x. And then the height of the shell at that point is given by the function value, f of x, with the differential dx. And again, to get the limits of integration, we're going to look at the region to be revolved. We're going to take the x coordinate of the very first shell on the left, the rectangle, and then the x coordinate of the very last rectangle on the right. In this case, it would start at x equals 0 and go to x equal 2. If we wanted to write this one down fully, we would then have the integral from 0 to 2 of 2 pi x, that's the circumference, times the height, which is 2x minus x squared, with the differential dx. In order to integrate, we simply multiply it out and then apply the rules that we've already learned. This would give us the volume of the solid, which you see created here on the right. Notice that this section does not touch the axis of revolution, though they connect at the bottom. That means that we're going to have a hollow cavity on the inside that's rather funnel-shaped, following the reflection of the curve on both sides. Let's take a look now at what it looks like in CalcPlot 3D. Again, you can see the shape to be revolved here in purple, and you can see a single shell that's been revolved. This is what it looks like with maybe 6 to 8 different shells revolved. And in the picture on the far right, you see the solid itself. You can still see part of the original area that was revolved sitting right here on this side, as well as a single shell that's been revolved. Let's look at it now on CalcPlot 3D. When I look at this, if I want to unrotate the representative rectangle, you can see the shape from which it came. Now let's rotate the region so you can see the solid itself. When you see this, do you see this sort of funnel-shaped interior? It's shaped sort of like a bundt cake, maybe. So it goes down in the middle and has a cavity, but on the very bottom, it does connect with the axis of rotation. So there's not a hole in the center. And the outsides are curving around, sort of like the shape of a gumdrop. Let's go ahead and tilt this one down so we can see that it's not hollow on the inside. The bottom of it, of course, is flat and circular because we are rotating from 0 to 2 on the x-axis, and the curve touches the x-axis all the way across. Let's now take a look at example 1. In example 1, we want to find the solid created by revolving the region bounded by y equal e to the negative x squared, y equals 0, the x-axis, x equals 0, the y-axis, and the vertical line x equal 1, and we're going to revolve it about the y-axis. We want to work this one using cylindrical shells. Notice that our axis of revolution here is going to be vertical. With the shell method, the double L, think of parallel. We draw our strips or rectangles parallel to the axis of rotation. This makes this narrow end of the rectangle the differential dx. Then we can look at the point where the shell is created, which is this point right here. When I look at this point, it has both an x-coordinate and a y-coordinate. The x-coordinate is actually giving me the radius of this shell. It's r on this side and r on that side. That means that r equals x. The height of the shell is given by the length or height of the rectangle. And the height of the rectangle is determined by the function, which is e to the negative x squared, and that becomes the height. Now we need to think about the limits of integration. We are having our very first vertical strip at x equals 0 and our last vertical strip at x equal 1. This was given in the boundary of the region. This enables us to go ahead and write down what the integral will be. We are going to integrate from x equals 0 to x equal 1, and we're going to have 2 pi r times the height times the differential dx. In this case, we have that the radius is given by x, and the height is given by the function e to the negative x squared. Don't forget the differential dx. Again, x is the radius, and the function is the height of the cylinder, which corresponds with the height or length of the rectangle. Now that we've written down the definite integral, go ahead and pause the video to compute it. Note that you will need u substitution. When I apply the u substitution, I set u to be the power on the exponential. Notice that the derivative of negative x squared is negative 2x, and I do have x as a factor inside the integrand, and it is a multiple of negative 2x. Then I abuse the notation by swinging the differential dx to the right. In examining my original integrand, I noticed that I have an x dx, so I solve for x dx to get du divided by negative 2. Then I'm going to replace the x dx with du divided by negative 2. Because I'm switching from x to u, I need to switch the limits of integration. When x is 0, a negative times 0 squared is still 0. Be careful when evaluating when x is 1. Remember that exponents have to be done before multiplication by the negative. So I get negative times 1 squared, which stays negative 1. When I substitute these limits of integration in, you can notice that they're backwards to what we normally expect. The lower limit of integration is higher than the upper one. However, I've got the negative inside here. The 2's will cancel, but the negative I can use to switch the limits of integration. Now I have the integral from negative 1 to 0 of pi times e to the u du. When I integrate and substitute the limits of integration, I get pi times the quantity, 1 minus 1 divided by Euler's number. This turns out to be very close to 2 cubic units. Let's take a look at what it looks like inside of Calc 3D. In Calc 3D, you can see the shape of the original integrand right here. We've got the graph of our function, and the next thing that we want to do is we want to revolve. When we revolve, we're going to take this shape right here and revolve it around the axis. When we revolve it around the axis, it will create an empty cylindrical shell, and we can rotate it forward so you can see that it's hollow on the inside. Let's go ahead now and let's unrotate the representative rectangle and instead rotate the region. When we rotate the region, you can see the shape that is created. Now, if you would like to see the more realistic shape, tell it to stop showing the end washers and you'll get a more realistic shape. Again, it is a circular flat bottom, and then it kind of comes up to a, well, like a dome shape. Let's now take a look at the next example. What happens when the axis of rotation is not one of the coordinate axes, x or y? In that case, we'll have to adjust the radius. The radius is going to be some expression of the variable in the differential, but it won't simply be x or y this time. Let's take a look at the volume of the solid created by revolving the region bounded by x squared, the x-axis, y equals 0, the y-axis, x equals 0, and the vertical line, x equal 1, about the line x equal negative 1. So our axis of rotation is not the x or y axis. In this case, it is still vertical, but it is not the y-axis. Because it's vertical, we're going to draw our shells parallel to it, meaning they're vertical too. That makes the differential on the short end dx again. When we look at this one, we need to figure out, based on the coordinates of the point where it meets the corner of the rectangle, what the actual radius is. Note that the radius goes from the strip to the axis of rotation. Measured from the y-axis to the region to be rotated gives us x. But the axis of rotation is 1 on the opposite side. You can think of this as x minus a -1, or you can just simply write x plus 1 becomes the radius. The height of the shell in the region that's revolved over here is again given by the y value on our function, which is x squared. This is going to give us the volume of a single shell. Remember that the volume of a single shell can be written as 2 pi r times h times the differential, and here it's dx. The radius this time is not simply x, but an expression involving x plus 1. The height is also an expression involving the variable x squared. Now that we have this part, we need to determine what the limits of integration will be. So we look at the very first strip, which is incredibly short, on the far left at x equals 0. And the last strip will occur on the far right at x equals 1. In order to set up our integration, we go ahead and integrate from x equals 0 to x equals 1 of 2 pi times the quantity x plus 1 times x squared dx. In order to integrate, you're going to have to multiply this out and then integrate using the normal rules for integration. I would factor the 2 pi out as a constant factor and leave it on the front while you deal with the integrand. Go ahead and pause the video now to work this one out. You can see here the image from Calc Plot 3D of what it's going to look like when it's revolved. Notice that the center of it, of course, is completely open. And this is because when we look at the picture again, we notice that the region to be revolved, which is this purple shaded region, does not touch the axis of rotation, x equals -1. There's going to be a hole in the inside. The outer edge, because of this vertical line, will be like a cylinder, with the inside sloping down towards that open circle in the center. Taking a look here at our definite integral, I factored out the 2 pi and I multiplied out the inside factors. This gave me x cubed plus x squared. And I used the power rule for integration, and I substituted the upper and lower limits of integration. Finally, you need to get a common denominator, which is 12. And when you reduce, you get 7 pi divided by 6 cubic units, which is about 3.67. Let's take a look at this one on Calc Plot 3D. You can see here the original region, which of course, and I'm having trouble getting it to go straight. There we go. You can see the original region here, x squared, that is going to be revolved. And we revolved one rectangle. Let's unrevolve the rectangle now. And let's go ahead and rotate the region. In this case, I'm using 12 shells. You can see as a dashed line the axis of rotation, x equals -1. If I tilt it down, you can see that it goes down in a sort of arena-like way, creating tiers all the way towards the empty circular opening at the bottom. If I tell it not to show the shells, it will instead go ahead and show me a translucent image of what it looks like. It is flat on the bottom and rather well ring-shaped. And on the inside, it creates part of a bowl, but it has an empty circle in the center. We now want to take a look at revolving about the x-axis. This is going to be very similar to revolving about the y, except to make our rectangles, our strips, parallel to the axis of rotation, they'll have to be horizontal. And that means the narrow end will indicate that the differential is dy. When we look at this, we can use the same idea of 2 pi times the radius times the height of the cylinder, then multiplied by the differential to get the volume of a single shell. In this case, we're going to have to rewrite it in terms of the variable y, since the differential is dy. We'll solve for x to get a function g of y. Then when we look at the strip, and let's draw a sample strip here in the region Q to be rotated. When I look at this, notice that the axis of rotation is the x-axis, which is here. And that makes this distance here the radius. But if I measure from the point where the strip is drawn on the function, this corresponds to the y value. Since the differential is dy, I will leave the radius represented as y. Now we need to think about the height of the cylinder. The cylinder itself has a height here, which corresponds to the length of the rectangle, just like when we revolved about the y-axis. In that case, we need to measure what this is. This, of course, is the x value, since it's measured from the y-axis to the point on the curve. But in this case, the differential is dy, so we have to represent this distance, which is the height of the cylinder, as x, but written in terms of y to square root of y. Now we can use that 2 pi RH formula to compute the area of that rectangular box and multiply by the differential dy to get the volume. When we do that, we'll end up with a shape that looks like this one here. Again, this curve right here is the function x, which is equal to a function of y, equal to 2 times the square root of y. When we look at this picture, the radius is the y value measured from the x-axis to the point where the rectangle intersects the curve. And the height of that shell is given by the length of the rectangle, which corresponds to x, which we re-represent as 2 times the square root of y. And you can see on the right what it looks like when we revolve it. Let's take a look at that one now. When we look at this one, you can see already that it does have this basic shape. Oops. Sorry, I need to click over here so it will rotate. There's the shape looking at it pretty much straight on. If I unrevolve the rectangle, you can see the region that is being revolved about the x-axis. Now let's go ahead and revolve all the shells by rotating the region. And we'll take the shells off so that we can see it. Notice that this does create a very similar shape to what we saw before, but in this case, the hollow space on the inside, while very funnel-shaped, is quite narrow as it comes down towards the point at the bottom. The base is again a flat circular region, and the outer edges of the solid are like a cylinder coming out because of the vertical line, or horizontal line rather. Notice that in the directions, we had to change, since the differential was dy, to x as a function of y. And then we wrote that the right graph was 2 square root of y, and the left graph was the y-axis, x equals 0. And we need to integrate from 0 to 4, from the lowest height of the strip to the highest height of the strip. And then we get our volume. Let's take a look again at the picture so that you can realize how to get the limits of integration. Our lowest strip is going to be drawn here at y equals 0. And our highest strip, well, I can't quite get it all on there, is going to be up here at y equals 4. And that means that the integral, in order to find this volume, would go from y equals 0 to y equals 4 of 2 pi times the radius, which is y, times the length or height of that cylinder, which in our case is 2 square root of y, with respect to y. In evaluating this integral, notice that you have multiplication between two factors that depend on y. You can write the square root of y as y to the 1/2, and when you multiply bases that are the same, you can add the powers. And this will give you 4 pi y to the 3/2 power. Then apply the power rule. Let's now take a look at the rule for revolving using cylindrical shells around the x-axis. In this case, we want to define g of y as a function of y, so this is actually the x value. Then the radius is given by y, the distance from the x-axis up, and 2 pi y represents 2 pi r, the circumference of the shell. G of y, which is x, represents the height of the shell, and dy is the thickness of the shell. And we integrate from the lowest layer, the lowest rectangle, to the highest rectangle. In example 3, we want to find the volume of the solid created by revolving the region bounded by x squared, x equals 0, which is the y-axis, and y equal 2 around the x-axis. It's very important to know which axis you're going around. Remember from our previous work with discs and washers that it completely changes the shape in most cases. Because our axis of rotation is horizontal, our strips must be horizontal, which makes the differential dy. Then I have to come to this equation for the curve, y equals x squared, and I have to rewrite it in terms of the variable y. Solving for x gives me plus or minus the square root of y, but this is the right arm, so it is the principal square root, the positive square root of y. This is going to give me the height, which of course is that x value that you see here in the central picture. The radius is measured from the axis of rotation to the location of the strip and is given by the variable y. And you can see the shape of the revolved region on the right. Let's go ahead and set up the integral now. We're going to go from a low rectangle at y equals 0 up to a high rectangle up here at y equals 2. That means our limits of integration go from 0 to 2. We need 2 pi times the radius times the height times the differential dy. In this case, the radius is given by just y, the variable itself, and the height is given by the square root of y. And then we have dy. Let's go ahead and combine our two factors of y. This gives us the integral from 0 to 2 of 2 pi y to the 3/2 power dy. You can think of the square root as the 1/2 power and y as y to the first, or 2/2, and 1/2 plus 2/2 gives us 3/2. Now that we have the definite integral written down, go ahead and pause the video to work this one out on your own. When we set this one up, we got 2 pi y to the 3/2 dy as the integrand. It's evaluated between 0 and 2. Notice that because the differential is dy, you again had to solve for x in terms of y. You get a plus or minus, but this is the right arm, which is the positive arm. Then when we apply the power rule for integration and substitute in the limits of integration, we end up with 16 pi square roots of 2 divided by 5 cubic units. Let's go ahead and take a look at what it looks like in CalcPlot 3D. In CalcPlot 3D, you can see the shell that's created here, and it's revolved around the x-axis. When we unrevolve it, we'll be able to see the region a little bit more clearly. Notice that we had to check the box for x as a function of y, and we had to enter the right function as the square root of y, and the left function as the x equals 0, the y-axis. Then our lowest horizontal rectangle goes from 0 to the highest rectangle at y equal 2. Now that you've seen the region, let's go ahead and revolve the whole thing. When we revolve the whole thing, we can see the shape starting to develop with the different shells. Notice that it is going to be flat and circular on the bottom because it was touching the y-axis at a straight vertical line. Now let's go ahead and take off the washers so we can see the true shape. When I look at this, I again see that funnel on the inside because the inside of it is hollow. It comes down to a point at the bottom where it is closed. Let's now go ahead and talk about integrating when we have regions that do not contact the axis of revolution, but this time for horizontal axes of revolution. Again, we're going to see that unlike the washer method, where we had to do an outer volume minus an inner volume, the shell method takes care of that cavity with the setup of the limits of integration and the representation for the radius and the height. In other words, it's sort of built in to the shell method. We're going to have to think about how to represent the radius and the height in terms of the variable that corresponds to the differential. Let's take a look at example 4 as an example of how to accomplish this. In example 4, we have a region that is bounded by the square root of x minus 1, the square root function shifted 1 to the right, and by y equals 0, which is the x-axis, and the vertical line, which is x equal 5. The purple shaded region here is the region we want to revolve. However, we do not want to revolve around the x-axis. We want to revolve around the horizontal line here at y equal 3. This line is the axis of rotation. This means that we're actually going to be reflecting this shape above it to see what the solid would look like. Because it does not touch the axis of rotation, just like with the disc washer method, I know I'm going to get a hollow cavity on the inside. Because this is a straight line parallel to the axis of rotation, I know the outer surface will be cylindrical. Go ahead and draw your rectangles parallel to the axis of rotation. For shell, we go parallel. This is going to give us horizontal strips, and the first one is going to occur here on the lower boundary, which is y equal to 0. So my first strip is going to give the lower limit of integration 0. Notice that the top strip is not up here at y equal 3. It is not at the axis of rotation. It is instead right here where this square root function meets the line x equal 5. We need to find the y coordinate of this point to know what the upper limit of integration is going to be. When we look at this, we can find this value that we have right here by writing that y, which is equal to the square root of x minus 1, and x equal 5 are intersecting. If x is 5, I can substitute it, and this will give me that the y value is equal to the square root of 4, which gives me the principal square root of 2. This means the upper limit of integration must be 2. Now that I know the limits of integration, let's talk about the radius and the height of the shell. The shell is going to spin this way around this horizontal axis of rotation. In that case, the radius is measured from the line y equals 3 down to the point on the curve where that particular rectangle occurs. So the radius is this distance. Let's see how to represent that in terms of the differential variable, which is y. When we look at this one, we're going to have to realize that the distance from the x-axis to the axis of rotation is a distance of 3. And the distance from the x-axis to the point on the curve where the rectangle occurs is a distance of y. That means that the distance from the axis of rotation to the point on the curve must be the longer distance 3 minus the shorter distance y. That makes our radius 3 minus y. Now that we know what the radius is, and it's represented in terms of the variable that represents the differential, we need a representation for the height. The height is going to be a little more complicated as well. When we look at the height here, notice again that the height of the cylinder is given by the length of the rectangle at that point. In this case, from the y-axis to the far end of the strip is a length of 5, because this is the vertical line, x equal 5. This distance from the y-axis to the point on the curve, the near end where it starts, that is a measure of x. But we can't have x in an integral related to y. So we have to rewrite our function in terms of y. So we solve for x. When we're looking at our function, we originally had y equal the square root of x minus 1. We need to write this as x equals something with y. So we square both sides to get rid of the square root, and then we'll add 1 to both sides. Oops, writing and talking. This gives me that x as a function of y is equal to y squared plus 1. That's not the height or the length of that strip. The length of the strip is the long measure 5 minus the x value. 5 minus the x value on the curve gives me 5 minus the quantity y squared plus 1. Then I can distribute the negative and combine the constants to get 4 minus y squared as the value of the height of the cylinder at that point. Now I have all the pieces I need to set up the integral. I know in this case that the height is 4 minus y squared, and I know that the radius is 3 minus the y value. I know that the lowest strip is at y equals 0, and I found that the highest strip was at y equal 2. Let's write down the integral now. This will give us the integral from 0 to 2 of 2 pi r h with the differential dy. In this case, our radius is given by 3 minus the y variable, and the height is given by 4 minus y squared, or 4 minus 4 plus 4 minus y squared. and the differential is dy. Again, my recommendation is to factor out the 2 pi as a common factor and then multiply together the two binomials. Pause the video now to work it out and then turn it back on so we can compare our results. I factored out the 2 pi and then I multiplied together the two binomials, which gave me a cubic function for the integrand. And I applied the power rule for integration and substituted the upper and lower limits of integration. When I simplified, I got 24 pi cubic units. When we take a look at this one, we're going to look at it in Calc Plot 3D. Notice again that because the strips are horizontal, the differential is dy. So we have to set it for x as a function of y. Here's what it looks like in Calc Plot 3D. You'll see that we've selected x as a function of y, and we've entered right and left functions. On the right, I have the vertical line, which is x equal 5. So it appears in the upper box. On the left side, I have the curve, which was the square root of x minus 1. However, because it is written as a function of y, I had to convert it to y squared plus 1. Now you can see here the revolved rectangle from one of the partitions, and you can see the dashed line, which represents the axis of rotation in the center of it. Let's unrevolve the representative rectangle now so we can see the full shape as well as the axis of rotation, and then revolve all of the shells. From the outside, it looks like a cylinder. But if we look at each side, on the back side, we can see that it actually has depth poked into it. Let's take off the shells so we can see a better picture of it. This time it is the right side that is flat, but it does have a hole, a circular hole in the middle. And on the interior, you can see that we have a hollow cavity corresponding to the shape carved out by the open space between the axis of rotation and the area to be revolved. And looking at it from the left side, we can see that it is hollow on the inside, but that the sides curve down towards the bottom. Now that we've looked at revolving with respect to both the x-axis, the y-axis, and lines other than the axes, we want to look at revolving regions that are bounded by two functions instead of one function. When we look at these, in the disk washer method, we needed a washer in order to solve this. However, the shell method takes care of that within the method itself. Again, it's going to affect the radius and height expressions for the shell method. Let's go ahead and look at example 5 so I can show you how this works. In example 5, we're starting with the region bounded by the power function y equal x to the 4th. This, of course, resembles an upward opening parabola, but it is much flatter at the bottom than a normal parabola, and it goes up steeper once it gets outside of the interval -1 to 1. The other curve is the sine of pi times x divided by 2. And you can see that one here in black. And it looks like a typical sine function. We want to revolve this around the line x equal -1, which is a vertical line over here on the left side. This vertical line at x equal -1 is our axis of revolution or axis of rotation. The region, which is bounded by the two curves and only the two curves, is the purple shaded region here. Because the axis of rotation is vertical, all of our shells must be vertical as well. We'll need to go from where those two first intersect to the last place where they intersect. Looking at this picture, we need to find an expression for the radius and an expression for the height. Let's look at the picture on the right. In the picture on the right, you can see the radius drawn to two different rectangles. In both cases, x is measured from the y-axis to the point on the function that is closest and where the strip is drawn. In this case, however, the radius extends from the strip all the way to the line y or x equal -1. That means the distance is x plus another 1. And that means that our radius has to be written as x plus 1. Can we leave it as x plus 1? We need to determine what the differential is. In this case, since the axis of rotation and the rectangles are all vertical, the differential is given by dx. So we can indeed leave the radius as the expression x plus 1. Now let's look for the height of the cylinder. The cylinders are going to be running this direction, which means that you're going to curve around this way. And because they're curving around that direction, the height is given by the difference in the y values between the two curves. The curve on top is always the sine function, and the curve on the bottom is always the power function y equal x to the 4th. That means that we can express our height here as the change in y values on the two curves. So this is going to be y on the sine function minus the y on the power curve. And we can represent that in terms of x by replacing them with their actual functions. Sine of pi x divided by 2 minus x to the 4th. This expression in terms of x becomes the height of the cylinder when it gets revolved in this direction. Now that we have all the pieces, let's think about what, in fact, our limits of integration would be. To find the limits of integration, I'd have to set them equal to find it. In this case, setting the two functions equal to each other and solving would be rather difficult. So I sort of cheated and simply used Desmos to tell me that the x coordinate where these 2 points intersect here is 1. I don't remember exactly what the y value was, but I believe it's also 1. Let's take a look and see if that makes sense to us. If x is 1, I have the sine of pi divided by 2, which is 1. And if I replace x with 1, I get 1 to the 4th, which is also 1. And then they're equal to each other. And that means that when x is 1, the y value on both curves is 1. So the ordered pair is indeed 1, 1. Now what I want to do is go ahead and write the integral. When I write the integral, we're going to have the integral from x equals 0 to x equals 1. And then we have 2 pi times the radius, which we found to be x plus 1, times the height, which we found to be the difference between the y values on the two functions. Once we have that, we multiply by the differential, and then, of course, we would evaluate. However, in this case, when we distribute, we're going to get x times the sine function. And until we have integration by parts, we're not going to be able to complete this definite integral. We can, however, take a look at what it looks like on CalcPlot 3D. When we look on CalcPlot 3D, we'll see, oops, I think I've got the wrong one up, right here, the sine of pi x divided by 2 as the upper curve, and x to the 4th is the lower curve. One cylinder, one cylindrical shell has been revolved around the vertical line x equal -1. In this case, because the strips are vertical, the differential is dx, so I select y as a function of x. And then I look for the function above and the function below. Above is the sine function, and below is the power function. Then I set my limits of integration from 0 to 1, and note that the axis of revolution is x equal -1. Let's unrevolve the representative rectangle and then revolve the whole thing. Notice, because it does not touch the axis of revolution, that we do have hollow space on the inside. When we take off all of the shells, we can get a slightly better view of what the final shape looks like. And I'm going to have to scroll to get it to blow up a little larger. All right. When I'm looking at this, I can actually see the original area that was revolved and one of the rectangles that was creating a cylindrical shell. Notice that it's solid on the edges, but it has this sloping funnel-shaped interior coming down to a completely hollow tube through the center of it. We now want to turn our attention to the next example, which is example 6. In example 6, we want to take the region bounded by the graph of y equal x, the identity function, and the graph of y equal x squared, the basic parabola, over the interval from 0 to 1. When we look at these, we want to find the volume of the solid of revolution when we revolve around the y-axis. In this case, we have two functions which are going to close off our area. The axis of rotation is again vertical, which will make all of the rectangles vertical as well, so the differential should be dx. Go ahead and pause the video to work this one out, then turn it back on so we can compare. This time, in order to determine the elements of the definite integral, I started with vertical strips that were parallel to the axis of rotation, the y-axis. The first strip occurred where the points intersected, and the last strip was also where they intersected. So I set the two functions equal to each other, and I solved. Do not divide by the variable. You will lose the solution x equals 0. I found two solutions, 0 and 1, which give me my limits of integration. Next, I need something to represent the radius and the height in terms of the differential. Because the rectangles are vertical, the differential must be dx. So I need to represent the radius and the height in terms of the variable x. The radius is going to be measured from the y-axis, which is the axis of rotation, to the strip, which is just, well, the x value on the curve, in this case on the line. But I can just represent the radius r with x. Now I need to represent the height or length of the strip. The height of the cylinder is the length of that rectangle. In this case, it's the y value on the line minus the y value on the parabola. But the line is y equal x, and the parabola is y equal x squared. So the height is the expression x minus x squared. Substituting these into the formula, 2 pi r h differential, I can distribute and apply the power rule for integration. After I substitute the limits of integration and simplify, I get pi divided by 6 cubic units. You can see the region here, and it's been revolved around the axis of rotation, the y-axis. When we're done, notice that it is going to meet at the bottom where the shape does touch the axis of rotation, but we'll have hollow space on the inside because this section does not touch the axis of rotation. Let's take a look at this on Calc Plot 3D. On Calc Plot 3D, we're now looking at this shape here. Again, because we're using the differential dx, you want to select y as a function of x. That means that we'll do the above function and the below function. Above, you can see that we have the line y equal x, and the bottom is the parabola x squared. We're going to revolve it vertically around our vertical axis of rotation. When I revolve the region, you can see it starting to develop. And notice that if you tilt it down and look at the inside, that it slopes down sort of like an arena, but it comes to a point at the bottom. It's not a funnel shape. It actually just gradually slopes about the same all the way down because it's coming off that line. If we take off the washers, then you can see the shape a little bit more clearly. Let me try to scroll in so I can make the picture larger. When I look at this, again, you can see the original region that was going to be revolved and one representative rectangle. You can tell that the inside hollow cavity is actually creating sort of a V shape that's been rotated in a circle. Let's now turn our attention to the last topic for this section. The last thing we need to discuss is, well, which method should you use? The disc, the washer, or the shell? In most cases, it's largely a matter of preference, whichever one you think will be the easiest to apply. There are occasions where one method is simpler to apply than another. There may even be occasions where one method is something that you can do now, and another is something you'll have to wait to do in Calculus 2. When we do this, if you always want to integrate with respect to the variable x, then you'll want to use the disc or washer method when you're revolving around the x-axis. Remember, in the disc or washer method, the strips are drawn perpendicular, which would make them vertical, so the differential would be dx. Then, to rotate around the y-axis or any other vertical line, you'll instead use the shell method, because in the shell method, the strips are parallel, which again gives you the differential dx. If you follow this protocol, you can always integrate with respect to x. But keep in mind that this does not mean it's always going to be the easiest way to go. Sometimes it is easier to represent the curve as a function of y as opposed to a function of x. This completes our discussion of volumes of revolution by cylindrical shells. If you're in Calculus 1, this ends the course and the end of the Calculus 1 playlist. If you're in Calculus 2, you'll have other topics, which are applications of integration, coming up next.